Hello students, in last lecture video we studied the isoparametric element, meaning that any irregular quadrilateral element, four noded quadrilateral element can be transformed to a square. So the original xy coordinates is transformed to the xi and eta coordinate system, where any irregular quadrilateral element is transformed to a square like this one. The stiffness matrix what we calculated is given by Kij equal to K minus 1 to 1 minus 1 to 1 then J transpose inverse of that, then del Ni over del xi and del Ni over del eta, transpose of whole of it multiplied by J transpose inverse of that, and then del Nj over del xi 1 del Nj over not xi 1 del xi and del eta, and determinant of the Jacobian matrix J, then d xi and d eta. Now we will just simplify it. So the transpose of inverse of a matrix is also equal to inverse of transpose of that matrix like this one. So both are equivalent. So we can also write it as A to the power minus t, meaning that is the inverse of A and also transpose of that. So since both are same, let's denote this is like this one. Also you know that transpose of A transpose of a matrix is equal to that matrix itself. So this is also the relation we will use here to just simplify it. So finally what we get K Ij is equal to, and a small k minus 1 to 1 minus 1 to 1. Now here transpose of whole thing. So one more relation we will use, like if C and D are two matrices, so transpose of that will equal to D transpose C transpose. So this also relation we will use that here in this case. So what we get? We get del Ni over del xi del Ni over del eta. So this is a vector, this is a 2 by 1 matrix. So transpose of that becomes 1 by 2 matrix. So here this is 1 by 2, then this transpose will go here. So this is J minus T, just to write like this one, write like this. So J minus T or transpose of that. Okay, so we have the first one, this taken care of. Now this one, so here we have J, let's write J minus T and del N J over del xi, also del nj over del eta, then j determinant and de xi de eta. Okay. So, what we see here, J inverse transpose. So, transpose of that is nothing but J inverse only. So, instead of this we can also write J inverse. So, what I meant is J of transpose of that will be equal to J inverse transpose, and transpose of that is nothing but J inverse only. So, finally, the k I j is given by a small k here, minus 1 to 1, minus 1 to 1. Then we have del n I, del xi, del n I, del eta. Then we have J inverse. Okay, then we have J inverse transpose, and then we have del n j, del xi, del n j, del eta. Then we have determinant of j, then de xi and de eta. So, this is the final form for Kij for the 4-noded 2-dimensional isoparametric element. Now, the next thing is how to integrate all these ones. So, let us assume f I j xi eta is equal to k multiplied by del ni over del xi and del ni over del eta, then J inverse transpose, then del n j over del xi, del n j over del eta, then J determinant, the whole thing let us call this is Fij. Then Kij is equal to nothing but integration. So, this is integration minus 1 to 1, minus 1 to 1, and then f and then Fij, then xi eta and dxi and d eta. So, this one. So, the question is how can you integrate this one. So, we will use the methods that we learned for one-dimensional finite element analysis. So, integration, if we know how to calculate, for example, I equal to f xi d xi from minus 1 to 1. If you know how to calculate this one using Gauss Quadrature method, same thing can be extended here to 2D. We will see how. If you remember the 1D Gauss Gaussian quadrature formula for integration of, let us say if you want to find out I equal to minus 1 to 1 f xi d xi. If you want to find out this one, so what we did this is equal to summation of wi f xi I, and what we did, we integrated it from I equal to 1 to number of Gauss points, so ng, like this one. So if you take number of Gauss points as 1, so if ng equal to 1, then we know that w becomes equal to w becomes equal to 2. So say w1 equal to 2, and xi 1 becomes equal to 0. So same if you apply here, so I becomes equal to w2 times f calculated at xi 1 is equal to 0. So I becomes 2 times function of 0, function fx f xi calculated at xi equal to 0. So this is what the I is. So if you take ng equal to 2, in that case we will have w1 equal to w2 is equal to 1, and xi 1 is equal to minus 1 over root 3, and xi 2 becomes plus 1 over root 3. So that means I becomes equal to f minus 1 over root 3 plus f 1 over root 3, and since w1 w2 equal to 1, so I am not writing it here. So I simply like this one, yeah. And similarly for I ng equal to 3, w1 is equal to 0, will be equal to 8 over 18, 8 by 9. So I will writing it here. So w1 equal to 8 by 9, and corresponding xi is equal to xi 1 equal to 0, and we have w2 which is equal to 5 over 9, and xi 2 is equal to minus root 3 over 5, and w3 is equal to also 5 over 9, and xi 3 is equal to root 3 over 5. So that really means I becomes equal to 8 over 9 function evaluated as xi equal to 0 plus 5 over 9 function evaluated at minus root 3 over 5 plus 5 over 9, again function evaluated at root 3 over 5. So like this. So same thing can be extended further for 2D problem. we are going to extend the one dimensional integration to the two dimensional integration that we need. So Kij we want to compute, integrate. So Kij is equal to, as we wrote earlier, this is minus 1 to 1 and again minus 1 to 1, and then we have a function Fij which is a function of eta, xi and eta. So d xi, d eta here. So let's call this one integration from here to here. So integration from here to here, let's call it g eta, and this function is f. So for us this one, call it f xi. In that we are integrating this with respect to xi, and then the whole thing will be a function of eta. So g eta, and then we will integrate it. What I mean to say is, the first thing f minus 1 to 1, that is z eta, will be minus 1 to 1, and then Fij xi eta d xi. So let's evaluate this one first. So this one, as we said, let's call it f xi, treat it like f xi, so that we will have integration equal to f xi I, not I, because we have already ij written like this. Let's call it m. So xi m. So m is equal to 1 to number of Gauss points. So like this one, or in other words, m equal to 1 to ng, and f xi is nothing like but this one. So Fij and xi m and eta, like this. So same thing here. So the whole thing is a function of eta now. Okay. Now coming back to here, so Kij, so Kij is minus 1 to 1 z eta d eta, where g eta is like this one now. So this applying the 1D integration using the Gaussian quadrature rule, what we get? We get integration or summation from let's call n. So n is equal to 1 to ng, and this will be sorry, here this should also have a weightage function. So we write w m with it. So here also there will be a weightage function multiplied like this. Okay. So here we will have w n, a weightage, multiplied by g eta, which is evaluated at nth point, like this one. So which is equal to summation n equal to 1 to ng w n. Now g eta n is from here we will get. So g eta n is nothing but you put eta n in this one and you get it. So g eta n means the whole expression, but eta is replaced by eta n. So, we will write the same thing. So, this becomes a summation m equal to 1 to n g f I j zeta m xi m and eta n, and multiplied by w m as well. So, like this one. So, this is the k I j. We can simplify further. We can also write it as this one as equal to summation. There were two summations now. Summation n equal to 1 to n g. Then we can also move summation this one here. So, we will have m equal to 1 to n g, and then we have w n, w m, and then f I j xi m and eta n, like this. So, this will be the summation of the whole thing. There will be two weights multiplied, one for xi direction, the other for the eta direction, and then f I j evaluated at the Gauss points. Okay. So, these are these Gauss points are equivalent to the one dimensional Gauss points. However, we will have Gauss points in xi direction and Gauss points in eta direction. Okay. So, this is how we can find out the integration for the two dimensional problems. I am writing it again here. So, k I j becomes equal to summation n equal to 1 over n g, and then m equal to 1 over n g, w n, w m, and here is f I j, and then xi m and eta n. Okay. We can also rearrange it and even write like this one. So, m equal to 1, instead of writing n first, we write m here, m equal to 1 over n g, and then summation here also n equal to 1 over n g, and then w m, w n, and f I j and m and n, m n, like this also. Okay. So, that we have m and n, m and n, and m and n, like this one also we can do it. So, this is the final expression for k I j, or how, or any integration of f function f I j. Now, let us see at the some examples. Let us say n g equal to 1. So, in that case we know that w, if it were a one dimensional case, then w 1 equal to 2 we know, and xi equal to xi 1 equal to is equal to 0. Yeah, so this is in one dimension, in the direction of xi, and the second direction also this becomes is 1, which is equal to 1, and eta 1 is equal to 0, meaning that in that case k I j will be given as some, this will be just once because there will be only one point. So, there is, if xi eta, this is xi, this is eta, there is only one point at 0 0 basically. So, k I j m equal to 1 to 1, n equal to 1, eta n equal to 1 to 1, and then we have here W1 times W1. So, W1 is 2 only, and so we have 2 and Fij at eta 1 and xi 1 and eta 1. So, it will be Fij at 0 0. So, this is what the integration will be. Now, if Ng equal to 2, then say in the xi direction, we will have W1 equal to 1 and W2 is also equal to 1, okay, and we will have xi 1 is equal to minus 1 over root 3 and xi 2 equal to plus 1 over root 3, and same thing is repeated for eta direction as well. So, for eta direction W1 equal to 1 and W2 equal to 1 and eta 1 is equal to minus 1 over root 3 and similarly eta 2 equal to 1 over root 3. Okay, so let us look at the figure. So, if this is the element, isoparametric element, where this is xi, this is eta, and what it means is it will have 4 points. Which all points? We will have one point here. So, this is here. So, there will be one point here, one point here, and one point here, and one point here. That is what it means. And where this will be 4 points. So, this point will be minus 1 over root 3, minus 1 over root 3 will be first integration point. The here is basically 1 over root 3 minus 1 over root 3, second integration point. Third integration point is 1 over root 3 comma 1 over root 3, and fourth integration point will be here, which will be minus 1 over root 3 and 1 over root 3. Okay. So, 4 integration point as we have seen here. So, the combination, so all combinations, so xi 1, xi 2 and eta 1, eta 2, they will combination. So, minus 1 over root 3 minus 1 over root 3 1 over minus 1 over root 3 and 1 over root 3, that is 2 combinations from here, 1 over root 3 minus 1 over root 3, third combination 1 over root 3, 1 over root 3, fourth combination. So, 2 times 2, there are 4 combination. So, this is how the integration points will be, and weightage is 1 for all the cases. So, hence the Kij, we can write it at Kij equal to going back here, this becomes W1 times W1, then will be W1, W2, then W2, W1, then W2, W2, W2. So, in all cases this is 1 only, because both of them are 1. So, we will not write it here. What we can write, there will be 4 terms because of that, and each term corresponds to one of these integration points. So, there will be 4 points corresponding to these 4 integration points. So, Kij will be equal to nothing but Fij, then evaluated at the first integration point. So, minus 1 over root 3 minus 1 over root 3. So, it is a comma, okay. Then plus second integration point. So Fij integrated at second integration point. So this will be 1 over root 3 minus 1 over root 3 third integration point plus Fij 1 over root 3 1 over root 3 and plus the fourth integration point Fij multiplied by Fij evaluated at minus 1 over root 3 comma 1 over root 3. So this is how the Kij will be calculated. Before we move, we want to make a correction here. So Kij should be W1 times W1 times Fij xi 1 eta 1. So where W1 is equal to 2. So we should have here 2 times 2 and then Fij evaluated as 0 0. But I wrote just 2. So here this should be corrected to 2 multiplied by 2. So it should be total 4. Yeah. So basically this should be equal to 4 F I j 0 0. Okay. For if we take Ng equal to 3, then there will be 3 times 3 equal to 9 integration points. So if this is the isoparametric elements in xi and eta coordinate system, so there will be 9 integration points. So integration points will be like this. So one here, one here, one here, then similarly one here, one here, one here, and one here, one here, one here. So there are 9 integration points, and we know that for Ng equal to 3 we have W1 equal to 0, W2 W1 is equal to 8 over 9, W2 is equal to 5 over 9, and W3 is equal to also 5 over 9. Corresponding xi, so you can write xi 1 is equal to 0, xi 2 equal to minus root 3 over 5, and xi 2 is equal to plus root 3 over 5. Okay, and then xi, then eta 1 also similarly 0, eta 2 equal to minus 3 root 3 over 5, and eta 3 is also equal to root 3 over 5. So this is the values that we have to use in order to integrate. So we can write Kij is equal to, now summation, so this will be the combination of this one. So this will be W1 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 W2 W1, so there will be 9 combinations. So we write W1 W2 and then Fij zeta 1 eta 1, okay, then plus W1 W1 W3 Fij xi1 eta 2 sorry W1 W1 here also W1 so eta 1 xi1 eta 1 so W1 W2 xi1 eta 2 plus W1 W3 F ij zeta 1 xi 1 eta 3. Now W2 W1 Fij xi 2 eta 1 and so on. There will be 9 terms. So I have already written 1 2 3 4 terms, there will be 5 more terms. So that is equal to, we can write W1 and W1, so 8 over 9, so write 8 over 9 square, and Fij, so Fij at xi1 eta 1, so xi1 is 0, eta 1 is 0, so write 0 0. Then W1 is 8 over 9 and W2 is 5 over 9, so 5 over 9 Fij, and then xi1 is 0, so xi1 is 0 0, and eta 2 xi1 eta 2 is minus root 3 over 5, so like this one. So this point is nothing here, this is the first, this point we are talking about. So this point is the, this point, this one. Now 0 minus root 3 over 5, so this is the, this one we are talking about. So sorry, this is 0 minus root 3 over 5, so this is not this but this point we are talking about right now. So this Fij 0 minus root 3 over 5 is this point, okay, plus 8 over 9 5 over 9, again because W3 is also 5 over 9, and Fij 0 root 3 over 5, so we are now 0 root 3 over 5, so this point we are talking about now. So this is what this is, okay. Then this term, so plus W2 W1, so W2 is 5 over 9, so 5 over 9 multiplied by 8 over 9, okay, times Fij and W2, so here should be xi2, so xi2 minus root 3 over 5, so minus root 3 over 5, and this is eta 1, so eta 1 is 0, so comma, this will be comma 0, okay. So minus root 3 over 5 comma 0, so minus root 3 over 5 comma 0, so this is the point we are talking about now, this point, and so on. The next will be this point. So we started by this one, then we use this one, then this one, then we use this, so next will be this one, then this one, then we will do this, then we this one and this one. So you can do in any order as long as the corresponding weightages are consistent. Other terms can also be written, but I am leaving this on you. not to forget, here Fij, is equal to we have k here, small k, multiplied by del n I del xi del n I del eta. Then we have j inverse, then j inverse transpose, and then we have del n j del xi del n j del eta, and the whole thing multiplied by remnant of j as well, where j is equal to a matrix which is del x over del eta, del xi, then del x over del eta, then del y over del xi, del y over del eta. So this is J, or Jacobian matrix, and this we need to evaluate, although we already have idea, but in terms of x1, y1, x2, y2 and so on, we have to find out J. This is what we will do next. So we have x is equal to summation of n I xi eta multiplied by x I, where I equal to 1 to 4. So there are 4 nodes. So if this is the quadrilateral, so x1 y1 is here, x1 y1, x2 y2 coordinate for the second vertex, then x3 y3 third one, x4 y4 is the fourth one, then x is given by this, so x1, so that really means equal to x1 n1 plus x2 n2 plus x3 n3 plus x4 n4. So we can write it as n1 n2 n3 n4 and multiplied by a column vector x1 x2 x3 and x4 here, like this. And similarly y is also can given by n1 n2 n3 n4 and x1 y1 y2 y3 y4. Okay. Okay. So next is we have to find out del x over del xi, because the Jacobian matrix has this term, so we will find out this one. So this really means this will be equal to del n1 del xi, because only this is a function of xi and eta, so that's why. So del n1 del n2 del xi del n3 del xi del n4 del xi multiplied by x1, x2 and x3 and x4 like this. And similarly we have for del x over del eta will be the similar term here. So in fact we can write it like this one, del x over del xi del here we want x over del eta we write it here. So and here del y over del xi and del y over del eta. So this, which is J transform, will be equal to nothing but del n1 del xi del n2 del xi del n3 del xi del n4 del xi. Similarly here del n1 del eta del n2 del eta del n3 del eta, then del n del n4 del eta and multiplied by x1 x2 x3 x4 and y1 y2 y2 y3 and y4. So we have combined it. So this is just for one example, and we extend it further to by replacing xi with eta, then replacing x with y. So we have this combination. If you want del x over del xi, then we have this row multiplied by this column. If you want del y over del xi, then we have this multiplied by the first row multiplied by the second column. If you want del x over del eta, then you have second row multiplied by first column here, and if you want del y over del eta, then you have second row multiplied by the second column here. Okay, so this you can recognize this as a transpose, J transpose. So this is J transpose. So basically this is equal to J transpose. Okay, now x1 y1 x2 y2, these are the coordinates of all the 4 nodes. These are explicitly known because we have n1 is equal to, if you remember, 1 plus chi multiplied by 1 plus eta, and sorry, this is minus 1 minus 1 minus. So let us write it here. So n1 equal to 1 over 4 1 minus xi 1 1 over xi multiplied by 1 minus eta. So that when eta equal to minus 1, xi equal to minus 1, eta equal to minus 1, this n1 is equal to 1, otherwise this value is 0. So you know that if n del n over del xi will be equal to nothing but 1 over 4 1 minus eta. Similarly, del n1 over del eta will be similarly 1 over 4 1 minus xi, and so on. So that means del n I over del xi can be similarly found out. So that means what I meant is this matrix is known. We just calculated del n1 over del xi, and which is equal to minus 1 over 4 1 minus eta, and similarly we get all these values which will be a function of either xi, every one of each will be a function of either xi or eta. So this is known, this is also known, hence this this matrix or the Jacobian matrix is a function of xi and eta, and which is actually known. For n1 we have the two derivatives, similarly for n2 we can find out, and so on, just to make it complete. Thus the Jacobian matrix J is a function of xi and eta, okay, and includes actually also a function of of x1 y1 x2 y2 and so on till x4 y4, okay. So since x1 y1 x2 y2 x3 y3 x4 y4 all are known, so J is a function of xi and eta. So xi and eta, for different xi and eta the matrix J will be different, where J is equal to transpose of J transpose. So this is J transpose, we have here the whole thing. So this is J transpose. So if you want to find out J, so transpose, further transpose, that's why I wrote J equal to transpose of J transpose, like this one. So just to sum up, we had Kij which was equal to, we have small k, so minus 1 to 1 minus 1 to 1, and we had del ni xi del ni del eta, then we had J inverse transpose, then multiplied by del nj del xi del nj del eta multiplied by determinant of the Jacobian matrix d xi and d eta. So here J, we know that J transpose has this expression. So x1 y1 and so on are known, and it has derivatives of n with respect to xi and eta, and derivative of n with respect to xi and eta can be calculated like this one, because we have n1 as an explicit function of xi and eta. So, for n1 here you see the example. Similarly, we can do it for n2, n3 and n4. So, that means since these derivatives are known, are function of either xi or eta, so the whole matrix is known, and since this is also known, the multiplication is also known, which is the J transpose. So, that really means J is known, which is a function of xi and eta. J and hence J inverse is also known, J inverse transpose is also known. These are also derivatives which can be calculated the same way as we calculated here. So, and this is also known. Determinant of this Jacobian matrix is also known because J is known. So, that means if you see at the integrand, everything is known as a function of xi eta. So, this can be integrated with respect to xi and eta, and hence we can find out the stiffness matrix.